Hello, welcome everyone. Sorry about the third videos. After I make the second videos and realized that the Monday class actually also have to, we need to discuss a little bit of the concept in section 13.1. Otherwise, we're not able to finish the whole thing according to our schedule. So hence the third video. So as I keep mentioning, you should watch others and get familiarized with others concept before our class on Wednesday. So you can do it on Tuesday, or you can even do it on Wednesday before class, okay? So we are going to briefly talk about this new concept in section 13.1, which is vector functions. So let me quickly talk about this, and to point out that from all the things that you have learned in high school, the functions that you have seen is the functions that looks like this, for example, okay? This is a type of functions where your input is a real number and your output is also a real number. If you write in interval form, this is going to be something that is like this, okay? Now, so this is a machine. As you know, functions can think of it like a type of machines where you put an x inside here. The output is x squared, right? So the output is going to be like x squared plus 1. If you put a 2 in here, the output is going to be 2 squared plus 1, which is 5, and so on and so forth. Now, the type of new functions that you'll be going to look at, we're going to be looking at a lot of different type of new functions in 251. One of them is going to be what we call a vector value function. So the input is still a real number, but the output now is things like, say, ti, right, plus 2j plus t squared k. So this is going to be a vector. So the input is a real number, but the output is a vector. And again, because our shorthand notation for this is t to t squared, so we're going to see that the output is no longer a real number, but something with these three components, with the I, with the j, with the k. So this is a type of what we call vector value functions. And you actually have already seen this type of vector value functions before. Just haven't kind of like emphasized the fact that this is vector value functions. One of the things that you have seen is the following. So this is, let's say, 3, 1, 2, all right, plus t, and then 1, negative 1, 3, for example. So this is an example of a vector value functions, which you know give you the equation of the line. So this, remember that if you put a 0 in here, your output is 3, 1, 2, right? So this is a position vector for a point, all right, at 3, 1, 2, right? So this is, again, this is not the coordinate, right? So this is 3i plus 1j plus 2k. So this represents a position vectors that is pointing from the origins to this point. So that is what happened at R0. And if you put R1, then you will get a different vector and so on and so forth. So if you trace this all out, the point, given those position vector, you will get an equation of the line. Let me show you a picture here. Right, so you can see that this is in one such example. The t here can change its value from -5 to 5. And you can see that if you put a t, let's say, equals to -5, let's see whether you can see this thing, right? You will see that the output of this functions is going to be a point, which is here, and then they give you the position vectors of that point. And then if you slide, constructed a slider, so when you keep sliding this, you can see that the vectors giving you, the functions, right, the vector value functions, give you the output as a vector. The vector is a position vector pointing to that the point, right? So you can see that while changing your t value, you can see that they give you the position vector of that point that is on the line. Okay, so this is a type of vector value functions. Input is the t. Look at it here. Look at the slider, right? So the input is a t, is a value. If it is not a real value, if it's something else, you cannot just slide it like that, right? So from -5, and then you keep changing the t value, keep changing the input. The output is always the position vector you are seeing right here. So this is something that we know. This is a type of vector value functions, okay? And one such typical example will be the equation of a straight line. Okay, so now in general, it doesn't have to be a straight line, but what happens is going to be this. We can interpret our vector value functions like this. So if you have an r, okay, it doesn't have to be t either. This can be just a number, it can be represented by any dummy variable. So let's say now I have something that is like t squared and then 1 plus sine t and stuff. So sorry, s, right? S squared, right? 1 plus sine s, and then every time you change your s, you're going to have something that's pointing to that, right? So for example, r0, this is something that we know. We don't have to worry too much about it. So it will be 0, 0, sine 0 is 0, and then plus 1 is 1. So actually, at time s equal to 0, it will be pointing to here. And then when s changes, we'll have to kind of like use computer systems to kind of plot everything out, because it's not easy to see what it will go. But suppose it would go here, it would go here, it would go here, it would go here. And then if you trace this out, all this point that are on that curve, right? So this is going to be a type of space curve. So this is going to be a type of space curve. So the vector value function, it has a direction too. So for example, s is equal to 0 is here, and then s equal to 1 is here, s equal to 2 is here. So it also gives you a sense of directions of how the curve have been traced out. So the vector value functions that you've seen over here, they give the vector, but if you interpret those vector as a position vector of a point, and then you connect all the points together, you get an example of a space curve. So the example that we saw earlier, the lines, the straight line equations, that is an example of a space curve, right? So straight line equations that we saw earlier, this is an example of a space curve. Okay, so let's look at some other stuff that we need to know how to construct a space curve. So let's start with something that is a little bit straightforward. In your notes, let's look at your notes. In your notes, this is they started with an example which is complicated. You don't really know how to sketch this unless you're using a computer system. But we have this example where, as already mentioned, example of a space curve. When you have, okay, let's quickly mention this a little bit. So when you have equations like this, okay, when you have an equation like this that has only I and j component, you know that the space curve is going to be always on a plane where the k component is 0, right? So there's no k component. So this is plus 0k. That means that all this thing here, space curve, is going to be on the xy plane. All right. So now I would wanted to talk about a special case of space curve that is on the xy plane. Let's build this concept up little by little. Okay. So we don't want to go immediately to something that is complicated. So let's look at, for example, a very simple example. Let's just restrict ourselves on the xy plane first, okay? So we can have, okay, y equals to 2x plus 1. So nothing special. This is something that you are comfortable with. Suppose I wanted to change this whole setup into a vector function. So what I'm saying is that I wanted to create a vector. Okay, so I wanted to create a vector where the output, there's no z component, so the output is always something I and then something j, and when I changes my t value, I will get vector that is pointing it here like that, here like that, here like that, and so on. So I will get all this point, right, by using this setup. Does that make sense? So I want to write a vector value functions, input real number, output vector, so that the output can be interpreted as the position vectors of the point that's on this straight line. Okay, so how do we do that? Obviously, we can because this is obviously one very simple example of the general space curve that we already know. So we can do the usual one. We can say that okay, we can find a point that's on the line. So obviously 0, 1 is one such point that's on the line, and we can think of it like that, okay, in order to use the knowledge that we have before. So we have a point that's on the line, and then we need a direction vectors, right? We need a vector parallel to this line, and we can get that from the slope. How do we get that from the slope? Well, you can think of it like this. If I move 1 unit here, right? If I move 1 unit here, I will have to go up 2 units. So my slope, okay, my directional vectors can actually be given by something that is like this: 1i, and then 2j, and then 0. So this could serve as our vector that is parallel to this line. Does that make sense? So, okay, let me say it again, right? So we all know, so if this is 1 unit, this will be 2 units. That's the concept of a slope of 2. So this moving, you can also now think about moving in this direction 1 unit, moving in that direction 1 unit, that will be 1i, because you're in the direction of x, and then you move 2j, right, like that. So the resultant vector will be this, right? So 1i, let me make this bigger. Okay, so is that up? Okay, so here 1i, 2j, 1i, 2j. So 1i plus 2j is going to be this vector that you have here. So that vector obviously is going to be a vector parallel on the line. And then now we can use the setup that we have before, right? We can use the setup that we have before. We can write RT to be 0, 1, 0, right? Plus T, and then 1, 2, 0. Okay, so if you ignore the K, because there's no K component here, so you can simply write this as our x equal to 0, y equal to 1. Yes, okay, so we'll write our equation here simply as t, okay, and then 1 plus 2t, and then 0. If the context is clear, you can even drop this and say, we're looking only at ij component. But it's okay to leave it like that as well. So that is the general way of us writing the this particular straight line equations, right? By using vector value functions. Okay, so that's one way to do it. The reason why we do it like that is because we want to look at as a generalization, as a particular case of a general linear equation, the general straight line equations that we have earlier. But we can do it in a much more easier way. We can also say that the whole idea about a straight line is that we can represent everything in just one variable. So let me say it this way. You can say that, okay, let me say that my x now is t. So what should be my y? My y is going to be 2t plus 1. So that is my y. So x is t, y is 2t plus 1. And since we know all this point xy, if the coordinate is xy, the position vector is going to be xy like this. So we know that our RT, right? If the coordinate is xy, the position vector is xi plus yj, right? So we are going to just simply say this is t, that's my x, and then that's my y, 2t plus 1, right? No z component, and we get exactly the same answer also. So that is different way of writing the same answers. Does that make sense? Let me say that again, right? So if you have a point here, coordinate is xy, we know the position vector pointing to this is xi plus yj. So shorthand notation is like that. So I know my x is t, y is 2t plus 1. We can write it like that. Okay, so that should be easy. Now let's do something a little bit more complicated because we need this. We need this idea. This is one of the idea that we'll be using a lot. Okay, so now let's say I have a circle, right? We know the Cartesian coordinate system give you this. This is a circle, center at the origin, radius 1, okay? So let's make it radius 2. So it'll be like that. So this is going to be 2, right? And this is going to be 2 and so on. Now I wanted to write down, okay, an equation. Z component is, the Z component is 0. We are on an XY plane. What should I put in here so that the result of this is a position vector that is pointing here, and then 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 pointing here, and so on, all the way to here, and then get back again to this point. All right, so basically, right, we are going to create vector value functions where the output is the position vector that is the position vectors of points that's on this circle. All right, let me say it again. So I want you to construct a vector value functions, okay, which means that I do know how many I, how many j you need in order to have R0 pointing right here. So R0 is a vector, and the vector has magnitude and directions. So the magnitude is obviously 2, direction in the j direction, so this is like this, okay? We can also agree that, nah, forget about that, and just keep on writing everything in 2 components, okay? And then when I have R equal to something else, I would like it to be here, and so on. So this is one of the very common things that we need to know how to do. So the idea is to utilize, so the idea is to first think about what should go into the x and what should go into the y, right? So that everything is controlled by a single real number. So here you have x and y. I don't want that. I want something to be only in t, something to be only in t, and then can still give this thing moving like that when my t changes. Okay, so in order to do that, we will have to remember one of the very important equations, which is that your sine squared theta, doesn't matter, okay, cosine squared theta plus sine squared theta, right, this is equals to 1. Okay, cosine squared theta plus sine squared theta is equal to 1. Everybody knows that. This is true for all theta. That's the reason why sometimes old books, they write this as an identity. Identity is not the same as equation. So x plus 1 equal to 2. This is an equation where there's only one x value that can make this true. Okay. Identity, on the other hand, right, means that this is not only true for theta equal to 0. This is true for theta equals to 0.1, 0.5, 2 pi, 7.6 pi, and so on and so forth. All the possible real numbers. This is always true. So that's called an identity. Now, how do we make use of this in order to get this answer? Right, so what we're going to do is we're going to do the following. I am going to write my x equals to 2 cosine theta. I'm asking you to do t, so let's use t. Okay, and then y equals to 2 sine t. If I have that, okay, if I write it like that, okay, and you don't have to make this so big. Let me this small. So x is equal to 2 cosine t, y equals to 2 sine t. If I write it like that, isn't it that my x squared plus y squared now is going to be, right, what is it going to be? It's going to be 4 cosine squared t, right, plus 4 sine squared t, and I can factor out my 4 and get cosine squared t plus sine squared t, and then that is going to be my 2 squared, right, which is exactly this. So if you write it like this, okay, and think about the positions, right? So the position, if you put this is like 2 cosine t, right, comma 2 sine t. This is going to be the coordinates for the point that's on the line. So again, if this is the coordinates on the point that's on the circle, and the position vector for this is going to be so many I plus so many j, right? It's going to be so many I plus so many j, shorthand notations, x, y, right? So this is going to be the position vector pointing to that. Knowing that, we are now ready to claim that if you write this as 2, okay, cosine t I, right, plus 2 sine t j, right, input real number, outputs vector. So what you are going to get is the following. Okay, let me just get out of this mess. So right here, 2, 2, y, x. Okay, let's do that one more time. I'm saying that this is 2 cosine t, 2 sine t, all right? So if my t is equal to 0, I will have this coordinates, this position vectors 2, 0. So where is it? It's pointing right here. Okay, for example, let's do something easier. All right, so r, okay, pi over 4. So pi over 4, this is going to be square root of 2 over 2, right? And then this is going to be square root of 2 over 2, right? It will be pointing like that right here. And r equals to That will be the position vector. So r equals to, sorry, t equals pi over 2. So I will have 2. So this one right here, cosine pi over 2 is 0, remember? Right, so cosine pi over 2 is 0, so the 0 sine pi over 2 is 1. So times 2, it will be 2. So now I will have this one right here. So now, if you changes the t, you see that your position vector are pointing to all this point, okay, that's doing all this stuff. And not only the thing will trace out a circle, it gives a directions, meaning that the point that been traced out is like in this direction. So now this is a vector value functions where the vector value function where the output is a vector, but if you think of the vector as a position vector of some point that is on xy plane, then those points will trace out a circle, center at the origin, radius 2. So you can consider this, okay, as a space curve. So it's not the same as this though. So this is another thing I want to point out. When you write down equation x squared plus y squared equals to 4, or you write out this is 2 squared, it gives you the circle immediately, right? If you write this in the computer program and ask them to plot this, it just pops up like that. But when you write RT equals to 2 sine t, okay, 2 cosine t, right, 2 sine t, and what you get is that it will give you a slider t, right? And then if you increase the value of the t, it will trace things out like that. So you actually see the tracing, okay? And this is an example of a space curve. All right, so we will, on Wednesday, we'll build on more on this concept because this is the starting point of something that is a little bit more complicated. So I want you to have this idea first before you come to class on Wednesday. Finally, since we are here, I just want to show you some of the demonstrations that we have. This is, let me get this out of the way. Okay, so you can see there's a slider at the bottom, right? So if you slide this, right, you can see, okay, let's start from -4 and then keep on increasing the t value. So you can see that this is a type of functions. Output is the position vector RT. This is not a straight line anymore, as you can see. And then the output is a position vector that points to the points that's on this red curve. So they are pointing. The pointing is done by the position vector. And if you interpret just the coordinate, and then you trace out the coordinate, you get this kind of shape that we call helix. We can have other stuff as well. Where is it? Yeah, some of it is not that uniform, but you get the idea. This is all the idea about position vector is, sorry, you get a vector value functions where the output can be interpreted as a position vector. If you do that, okay, and then you connect all the coordinate that has been pointed by those position vector, it will form a one-dimensional curve in three-dimensional space that is called a space curve. All right, I will continue this and do more example. We have to develop something that's much more sophisticated than this because we need all this idea on Wednesday. This is really the last videos for the class that we missed on Monday, and thank you very much.